Florian Girelli from the University of Waterloo, and he will talk about Hopf algebras, QFT, or how to build topological invariants using QFT techniques. Thank you. Please.
All right, thank you. So first I wanted to thank Kurush and Dominique and all the other organizers for inviting me here to speak in front of you today. And I wanted to also apologize again for canceling at last minute last time. I got kids, and these days they're getting sick pretty easy, so it's pretty crazy. So I want to talk about some work that I've been doing with my PhD student, Matteo Laudonio, who defended actually last summer. And so Matteo has been working for his PhD on Hopf algebras, two group, and so on, so very abstract stuff. And now he's actually working for European Italian rocket, which is called Vega. So for the students who might be listening, I just wanted to highlight that even though if you can work on quantum gravity or Hopf algebra stuff, you can become a rocket scientist. So what I would like to talk about today is basically how we can try to use Hopf algebras, or actually what I'm going to emphasize a lot today is that we can use the notion of plane wave to define topological invariants and also use some structures from quantum field theory to achieve that. Okay, so the plan. So the first thing is that I will remind you quickly what are those topological invariants I'm talking about. That's going to be essentially the Turing model in 3D. So I will be working in 3D. I will try to, at the end of the day, to formulate that in terms of Hopf algebras. Then I will have a quick overview of why we can use Feynman diagrams to generate triangulations. And then I will try to merge these two concepts and use some Hopf algebra formulation of quantum field theory, just for example, Euclidian. And so I will try to define a scalar field theory, which Feynman diagrams I will interpret as generating triangulations, and we'll see that the amplitudes will be actually topological invariants. So that's the plan. So let's start with this notion of topological invariant. So by a topological invariant, here we have in mind the Turing model, or there is also its generalization, which is called the Barrett-Westbury model. And the construction of the Turing model is kind of categorical in nature. And what we're using, they were using the category of representation of UQ SU2, where Q is root of unity. And this representation, if you deal with a manifold, you can a 3D manifold, you can triangulate this 3D manifold, and you're going to decorate the edges of this triangulation with representations. And then with that in mind, with this combinatorial structure, we can construct a number. So that's going to be the part like the Turing model. And essentially, what we're going to do is that we're going to associate some weight to some structures. For example, if we have a tetrahedron, we're going to associate to the tetrahedron, we're going to associate the value of a 6G symbol, right? The 6G symbol is similar to, can be interpreted as a tetrahedron geometrically. We can also associate some values, some numerical values, always depending on the edge decoration, which are the representation. So we can also put some weight on the face and some weight on the edges. And so out of that, we are going to get what is called a topological invariant, which means that this is going to probe the topological features of the manifold. So as I said earlier, the model was defined for Q root of unity, and that's because then you get a finite number. But this model can also be extended to when Q is equal to 1. So basically, you would deal with representation of SU2, or Q being real. The issue, if you are a mathematician, is that then this is not a finite number that you will get. There are a lot of infinities. But if you're more of the physicist side, that is actually kind of still okay. And in fact, these divergences, we can really identify where they come from, and you can regulate them. I should emphasize that when Q is equal to 1, this model becomes a Ponz and Oriti model, which had been introduced in the 60s as a quantum gravity model by Ponz and Oriti. The Turing model is actually related to the Chern-Simon action and so on. And also you can, of course, then there is a relation with the Jones polynomial and so on. So what do I mean by topological invariant? It means that we know that there are some moves. If we have a triangulation, there are some moves that we can perform, which are called Pachner moves. There are other kind of moves, but the simplest one are the Pachner moves. And this Pachner moves, basically, if the number you built, like the number I built earlier, Girelli model, you know, if this number is not changing when you perform these moves on the triangulation, that's encoding the fact that you have a topological invariant. And so what are those moves? So we have two moves in 3D. And the first one is that you can have one tetrahedron, and you can put a point in there and build of this one tetrahedron 4 tetrahedra. Or you can start with 4 tetrahedra and kind of coarse grade it into one tetrahedron. And so here I just wanted to illustrate. So I can have, you see, I got here over there, I've got 4 tetrahedra, and I can basically merge them. I'm going to use technology here. Oops. So you see, I can merge them, and the fourth one is going to cross, and I'm going to get one. It's like the final one. This one, the one that I've got at the beginning. So I can merge coarse grain 4 tetrahedra, and also I can start with 2 tetrahedra and put a line in between for example, between this vertex and this vertex, and that would generate me 3 tetrahedra. And I can also do that with that. So I start here with 3. So this one does not work so well. There you go. So that's 2, and then I'm going to close it up, and that I merge here. I was able to merge a coarse grain 3 tetrahedra into 2. So if the number you built is invariant under these moves, then you have a topological invariant. Okay, so that's what happens. So this topological invariant can also be built from actions, and so like I said, the Chern-Simon action is kind of one of the leaders there. And here, during my talk, I will always have in mind the case where we deal with Chern-Simon with defined in terms of SL2C. So, you know, here I'm starting with my action as a Chern-Simon action is defined in terms of the Chern-Simon action, okay? And so it's with value in SL2C. And then what I'm going to do is that I'm going to break up this connection into 2 pieces. I'm going to have one piece into SU2, that's going to be omega, and one piece into this other piece, that's going to be the AN, some element in AN2. So this is the Iwasawa decomposition of SL2C. So SL2C, I can decompose it into a piece, a sub-algebra SU2, and another one AN2. So that's what I'm doing here. And now I can try to rewrite this Chern-Simon action in terms of these subfields, if you wish. If I do that, I get up to a boundary term. I get the so-called BF action. Okay, so that's the BF action, and what I do get along the way, you see that here I got some numbers which has the dimension of length, or 1 over length, and this guy is going to be interpreted as a cosmological constant, and I'm going to always work with a negative cosmological constant, because you see, if I had because of the definition here, if it was positive, I will get an I, and so things will become complex, and so things are going to be more complicated. So I can rewrite the Chern-Simon action in terms of a BF action, and this this happens to be exactly 3D gravity with a negative cosmological constant. So you could start with general relativity in 3D, go to the Baratin formalism, if you know the GR formalism. So you introduce the frame field and so on, and you will get this type of action. So that's why back in the days we then introduced we studied Chern-Simons and so on to quantize gravity. So I just want to emphasize some fact which I think is pretty important, which is that when we define this gravity theory here, we see that we do use a connection which is for SU2. So I'm dealing with Euclidean gravity. And the gauge transformation that we have and the structure that we have do not depend on the cosmological constant, right? That's just a normal gauge transformation that we have. Then it's known from the quantization of Witten and so on that at the quantum level, we're going to get a quantum group. And the deformation parameter, which is Q, is actually a function of the cosmological constant. So this means that at the classical level, we do have some symmetry structure which does not depend on lambda. And then at the quantum level, the symmetry structure is this quantum group structure, and it's parameterized by, it depends on lambda. So there is a big shift. There is kind of a big jump. And that's kind of strange in a way. I mean, because you expect when you expect that the symmetries at the classical level should kind of percolate at the quantum level. Otherwise, the quantization process is strange. So is there a real issue here? And in fact, there is a simple solution, a simple explanation, which is that the variables that I got or presented before are actually not the proper variables to characterize the quantum theory in terms of the quantum group. So I need to do a change variable in the action so that I'm going to have, at the classical level, I'm going to have transformations which depend on the cosmological constant, and so that at the quantum level, I also get those deformed gauge transformation. So we need to find the proper variables, and that's some work that I've been doing recently. And so this is just actually a canonical transformation. So that's just, from the phase space perspective, it's just a minor transformation. So it's not altering anything. So I'm just doing a canonical transformation. I'm just renaming what I call my connection. And so the connection now is going to depend on this vector n, and it's going to depend also on the frame field. And this vector n is actually a vector that depends on the cosmological constant. So now the connection is going to depend on lambda. And that is why then, if I quantize that, at the end of the day, I will get also a dependence on lambda at the quantum level. So if I'm doing that, I need to rewrite the action that I had at the beginning, in terms of those variables. So my punchline is here that this is a standard formulation of BF gravity, BF theory with a cosmological constant. And this is not the right variables which lead to the quantum group variables. And in some recent work, I showed how you can start from this action and really derive the quantum group structure, or at the classical level, the Poisson-Lie structure. Okay, so this is a quick overview of what's happening at the classical level in terms of action and so on. And you see, I just want to emphasize that this action is actually a topological action. In fact, you can check that there is no local degrees of freedom. So this action should be related. It is related to the Fourier model and so on. So that's what I want to talk about now. When lambda is not zero, things are getting complicated. Is actually the goal of what I want to do later on. So I'm going to focus first on the case where lambda is actually zero. And things are much simpler. So in this case, I'm just dealing with BF theory. That's just this guy, right? So we call it BF. Here B is E. That's because I use the frame field notation from gravity. And so how is this action? How do we connect that to the Fourier model? Or here, because lambda is zero, that would be the Ponzan origin model. How do we connect that? So we look at the quantum theory. So we look at the partition function. So we start with a given manifold, M, 3D manifold. Here for simplicity, there will be no boundaries. I don't want to go too much details. And so strictly speaking, That's the partition function, and very roughly, mathematician would be pretty upset with that. What I can do is kind of integrate over the E here, and I see this is like behaving like essentially like a plane wave, right? So I get some kind of delta function, and that's just, you see that this partition function is just saying that we want to look at the flat connection, right? So that's what it means. The curvature has to be 0. The delta function says the curvature has to be 0. So because we are dealing with a topological theory, we can deal with a manifold, or if we triangulate it, the triangulation has the same topological features as the theory, so there is no loss of information. So let's move to the triangulation, and so that we can smear the fields, we can regularize them by smearing them, just a bit like in gauge theory or in Young-Mills. You can also go to the lattice Young-Mills, you smear things so that things are kind of easier to deal with. So I'm going to triangulate my manifold, and I wanted to introduce some notation and some terminology. So we have the triangulation, and the triangulation is made of tetrahedron. Tetrahedron are made of faces, these triangles. These triangles have edges, right? And these edges are boundaries, are basically given by vertices. But then I need also to deal with the dual structure, because I will have to, there is a Poincare duality, so we will see that when we deal with the action. So if we have a tetrahedron, dually we're going to have a point, right? So a tetrahedron is going to be dual to a point, a node, what I'm going to call a node. Then a link is going to be dual to a triangle. And then if I have a face, that's going to be dual to an edge. And a polyhedron is going to be dual to a vertex. Okay, so that's just a Poincare duality. And I gave some examples. So here you see that here I got a tetrahedron, right? And I got the edge, the links, which are dual to the triangles. In the center, there is a node. And then I can glue that, and I'm going to create like that the one complex, which is dual to the triangulation. This one complex will soon be the analog of the Feynman diagram. So here in this example, I just glued 4 tetrahedra, and so the links, they go, then they share a face here. This tetrahedron share a face with this one, and the link just goes through one this face, this triangle. And so here in orange or yellow, that's basically the dual one complex. So I can smear the fields. And so the frame field is a one form, the B field is a one form. So I'm going to smear it over the edges of the triangulation. And then the connection is a one form too. So I'm going to smear it over a 1D structure, which is going to be the loop in. So I'm going to smear it over the links on the dual one complex. I'm going to do so because then if I want to talk about the curvature, I know that I can obtain the curvature if I consider a closed holonomy. Right? If I consider a closed holonomy, that's going to generate me the notion of curvature. So here I'm going to have a closed holonomy, and you see that from the definition of the action, which was EF, my action was like E wedge F. You see that's a free form. This is a one form. This is a two form. That they need to generate a free form. So this means that I need to use the Poincare duality, right? So they need to be discretized on dual structures. So the curvature is going to be discretized on such a face, and as I said, the edge is going to be discretized. Sorry, the frame field is going to be discretized on the edge. So this means that I can review this partition function of BF. I'm moving to the triangulation now. And now I just have either basically I can discretize this piece and say, oh, okay, you can, one can just, F, I said this is discretized as holonomy is closed around a loop. And so that's basically what I just encoded here. So we just regularize, and d omega is going to be regularized into dh. So dh is It's going to be the R measure. H are SU2 holonomies. And that's some kind of regularization or discretization of this quantity. And now we can also prove that if you do the partner moves on this expression, this would stay invariant up to some infinities, like I said, but we know how to address those. If we want to actually relate that to the Pons and Oriti model, we have to go to the representation picture. And so we, instead of considering the H, the group valued, what we do is we go to the representation picture. And so we can replace, for example, the delta function in terms of its expression in terms of characters and so on. Or we can use the Fourier transform, the Peter-Weyl theorem. So that's basically what I have in mind here. And at the end of the day, if you do that properly, starting from this expression over there, you will just recover the analog of the Turing model, but with Q is equal to 1, which is the Pons and Oriti model. And like I said, this is a topological invariant. So this is how this BF action that I told you about at the beginning can be related to this topological invariant that I started with before. And here I did it in a simple case where lambda is 0. So what happens if lambda is not 0? Then you see that now it's not anymore like a nice plane wave piece. There is this crazy volume term that spoils the nice calculation. And if you do, very rough, if you put that in Mathematica or whatever, that's what you kind of formula that you would get. So this you get an expression of as a Bessel function of the second kind. There is this complicated term here. So how can we discretize this piece now? Because this is not a delta. We get this Bessel function. So what's happening there? That looks pretty complicated, and I want to address this point. And like I said, I will always work with lambda negative, and so in the Euclidean case with SU2. So what we noticed before is that we can express this topological invariance in terms of delta function. And delta function come from plane wave, right? So, and plane wave then called the notion of duality. So maybe a way to address the generalization of that is actually to introduce a deformed notion of delta function. So that's what I'm going to do. That's the first thing. And the second thing is that I'm going to use the Feynman diagram structure to generate these amplitudes. And so I'm going to do these Feynman diagrams also in the case where I use quantum groups. So we know that.
Florian,
sorry.
Just a question. Could you return to the last? So what was this equality in quotation marks? Maybe I missed this point.
So it's just. So I just meant. So here I just. You see here when we do the calculation with this guy, you see that we can treat that as x. So it's like x at p, right? You can interpret that as some kind of plane wave, and say that this is like if I integrate over e, this is kind of a delta function for the f, and so then you can do something similar. So here you treat it as that's like, you could treat it as a function like x here at p, and then you have a x cube kind of x cube contribution with potentially with vectors. Okay, so something like that. And then what's happening? What is then this? What is the analog of that? What is if you were to perform this integration? So it's like I said, it's that's why it's in quote, right? It's not exact. Yeah.
Thank you.
So yeah. So like I said, earlier, the BF action is related to the Chern-Simons action, and when lambda is equal to 0, this is a Chern-Simons action defined in terms of the Euclidean group. And the Euclidean group, at the quantum level, it gives you like the Drinfeld double. So the key symmetry at the quantum level for the Euclidean group Chern-Simons is the Drinfeld double of SU2, where the dual piece of SU2 is trivial, just R3. Or that's U of, that's this structure over there. And so, as I said before, to define the topological invariant, the partition function, we had delta function, which are kind of related to plane wave. And plane wave are kind of the key tool into the notion of duality. And duality is a kind of a key notion key notion for quantum groups, right? Or especially in the case of Drinfeld double and so on. And so what we like to do now is to see if we can generalize this notion of duality of plane wave to the different case. And in fact, this has kind of been done in general by Majid and many other people, and I want to take advantage of that. So first, I'm going to start with a pair of algebras or bi-algebras, and then you can also make them of algebras. And then we're going to pair them. We're going to have some skew pairing. So we're going to say that they are skew paired. So you see that there is some kind of duality relation between them, right? That's this relation. And then we know that the product of one is going to be related to the coproduct on the other side. And that is these are the typical properties of dual of a pair of dual of algebras. And then if there is an antipode, it's going to have to satisfy this kind of these properties where you put the antipode on the other side, you get the inverse. And so Majid showed that then if you have a pair of dual of algebras like that, on bi-algebras, then you can actually put them together, form a match pair, and then that's how you can construct then the quantum double. And in fact, you can also then construct what you call the action, the action and the back action in terms of this pairing. So that's a general theory. And so we have a pairing, we have a pair of algebras, and then here we have this quantum double. And this quantum double, as I said before, this is a key structure behind the Chern-Simons formulation, and so the BF theory and so on. So, but now if we have a pair, we know that a pair of algebras. So can we actually find a map that takes one and to the other one, right? So, and that's typically going to be the Fourier transform. So let's quickly do a concrete example. If I look at the function over R, okay, so I'm looking at the function over R, that's going to be the algebra H, another function over R, that's going to be A, and then I look at the generators for this function. So I'm going to consider for the generators here, there's going to be the monomials in X, and this other one is going to be the monomials in P. I can set up a duality structure in between the two. Okay, so that's going to be my duality structure. And I should emphasize that these X and P are the coordinate function, right? So those are like functions. And so I got the duality. I know that these two structures, these two algebras can be dual to each other. And then I can construct a new element which lives in both places, in both H and A. And I'm going to call it sigma, and that's essentially what a plane wave. And so that's the sum over all these monomials. So that's Majid also in his book, he calls it, he sees it as some kind of identity matrix. And so that's exactly the plane wave. And this plane wave, we know that it satisfies some key properties. If you do the product, so product here with the same X, you see I've got a P1 and P2, then it's going to be the sum of them. And then if I have the same P, I'm going to X1, I'm going to have the sum of the X's here. So this is kind of the fundamental property of the plane wave. And then out of that, I can introduce the Fourier transform, which is a map that is going to take me a function in X and going to map it to a function in P, or vice versa. So that's a Fourier transform. And now we can actually make that very more general for Hopf algebras. So if we have a pair of co-paired bialgebra like that, then we can actually introduce an element now sigma. So now, but you see that sigma is now an element in in both copies, right? So it's a bit like the integral symbol. I mean, often it's kind of of algebras we use the integral symbol. It's a bit so I find it a bit confusing. But so anyway, so here sigma is going to be now an element in two copies, and so sigma is going to become the plane wave. And this property is exactly the property that I was telling you about here, right? And here, that's I've got these two properties. Just that now I'm talking about functions. So in my previous example, I had a sum P1 plus P2, but P1 plus P2 is, in terms of function, that's a coproduct. And that's why here I'm dealing with a coproduct. And I also, if there is an antipode, I'm going to demand that. And so those are compatibility properties. And so that's just encoding the properties, compatibility properties for the plane wave. And if we have the plane wave, then we can actually introduce a Fourier transform. And so you see that this Fourier transform is going to take an element in my first so here that's an element in H. Sigma is an element in H tensor A. So here I just put nothing in A, just one. And then I'm going to put a left co-integral. And I should emphasize again that in the Hopf algebra language, a co-integral is actually what we would call an integral in calculus. So we are integrating over the H sector. So that is killing the H sector, and we just have some component in the A sector. Okay, so that's going to be, this guy is going to be an element in A. So, and then you can define the inverse Fourier transform. And if you have the inverse Fourier, okay, so that's it's going to take an element in A and get an element in H. So there are some normalization factor. This normalization factor sometimes might be, so here we wanted to keep track in the full generality. But definitely sometimes you get infinities. And also I should emphasize that we never, here this was what we did is very algebraic. We never really took care, about norms and so on. Typically when you talk about Fourier transform, you want to talk about L2, L2 function, L2 function and so on. And so here we did not do that. So then you can prove that this Fourier transform, these two maps here are basically inverse to each other, and this was actually done in a specific language, a specific case, probably pretty general, but by Majid, and we just reformulated this, what he did in terms of the sigma picture. So if you have a plane wave, then you can also introduce a delta function, and the delta function is just the Fourier transform of the unit, the constant function 1. Okay, so that's going to be, we just doing the integral over the plane wave. That's going to be what we call the delta function. Okay, so then let's try maybe to make a bit of sense of that. So the key example that I was always using is the case of SU2. So we can deal with the function over SU2, and then dually we know that there is a pairing between with this function of SU2 and the developing algebra. It's like angular momentum, right? And so we can construct the plane wave in this case. So this is a bit like if you were doing T star of, so you're looking at the contingent bundle of SU2, T star of SU2, that's your phase space. And then you want to introduce a Fourier transform between configuration, which would be SU2, and momentum, which would be R3 here. And so, actually I used a different convention. I called the function over SU2P, and the function on R3, I call it X. Those are my coordinate function. I have to pay attention that because on SU2 is like a sphere, it's S3. So actually, if I talk about coordinates, I need to look at two patches. And so I would need, strictly speaking, to be careful about that. And there is this paper who people really describe in details what you're supposed to do. So, that's just a normal plane wave that you can construct here. And the properties that I was telling you about, the delta function, as I said before. Sorry, not the delta function, the coproduct. The coproduct is, can go in the exponent over there. And so these are functions, right? So I can evaluate these functions. That's typically how we formulate things. And to evaluate the function, I'm going to use the duality between functions, the algebra function and the group algebra here. So I'm just evaluating this guy, and you see that this is like the product of group elements, right? Because I know that the product on the group algebra, that's a coproduct in the function algebra. And this means that here, in this case, I would get a non-commutative addition of momenta. And so dually, this means that I get a star product for the X from R3. And then I can do the same thing for on the X sector. I can look at the coproduct. So these were the formula that I gave you earlier when I defined the duality between the Hopf algebras. And in this case, since I'm dealing with the group R3, it's commutative. And so I'm going to have the pointwise, commutative pointwise product on SU2. So then we can get back to this Ponzano-Regge model and try to say, okay, can we reformulate that maybe in the abstract nonsense language in terms of algebra language, so that then we can generalize that to the quantum group case, because we know that when lambda is non-zero, we get the quantum group structure. We get this deformed Drinfeld double. So, and here you see that it's pretty simple, because we just have delta function. We have an holonomy around the loop. This holonomy is a product of holonomies along each link, right? So I got each link. And if I get a product here, because it's a product, this means that in terms of the function, it's going to become a co-product. And so this means that we are doing the co-product on the plane wave, or on the delta function. So we can simply reformulate this delta over the product in terms of a co-product over the delta function. And now we are using the abstract nonsense language of algebras. And so with this formulation, we could say, oh, okay, then now we can try to generalize this formula. Instead of using the delta function on the Drinfeld double of SU2, the simple one is look at the Q deformed one. And that would be, because we know that from Chen-Simon and so on, that this is a relevant structure that is at play. And so this would mean that we need to find what is the plane wave structure when we deal with this deformed Drinfeld double. And here, like I said, it's always Q here. So let's maybe spend a bit of time on that. And so to formulate, what I want to do now is to give you this plane wave. So we found what was this plane wave in this case. And so for using that, there is for SU2Q, quantum group, we typically deal with this parametrization. And instead of using this parametrization for finding the duality between these two structures, it's actually more convenient to use Euler angles. And then in the same way, I'm going to rescale my generators for UQSU2, and I'm going to use instead the X and the H. And so then we can construct the duality structure between, so I'm going to, between the generators of the one of algebra and the generators of the other of algebra. And what are those generators? They are just monomials in the different coordinate function. So here I got the generators on the UQ SU2, that's X plus H and X minus. And on the SU2Q, that's going to be the Euler angles. So there is such duality, and the duality involves Q numbers or factorial of Q numbers. And with this duality, you remember, I can build the action of UQ SU2 on the SU2Q, the quantum group, and the back action. So that's the right duality. And then out of that, I can actually build, I can realize what is the right plane wave. And now to construct this plane wave, we use a bit of a mix. So it's a complicated formula, which is using some star product for the x and so exponential with the star product for the x sector, so the UQ SU2, and some Q exponential on the SU2Q piece. So we did that, Matteo found that after a lot of work, and then later on we realized that this was actually kind of done already by Fondal and Galindo in a different context. And so if we have this plane wave, then we can actually construct the delta function using the tricks I told you before. And so then this is kind of giving us a way to construct the Girelli model as a bunch of delta functions, which are this deformed delta function. So I could do that, and with this delta function, try to prove that this is a topological invariant. So I could stop here and say, okay, that's it. Now I'm going to construct my Girelli model in terms of plane wave. And that's, I think, one of the things I want you to remember, that we can construct the Girelli model in terms of a bunch of delta function or in terms of some plane waves. But what I want to do now is do kind of take a detour and use a bit more structure and use some quantum field theory techniques to build this amplitude. So how can we actually use Feynman diagrams to generate triangulations here? Well, it's actually pretty simple. So we are going to use this notion of duality and a Poincaré duality. And for example, if we deal with a phi to the 4 interaction potential, so then we know that the Feynman diagram is going to have 4 legs. And you see that these 4 legs, if you say that each leg is actually dual to a triangle, right? Then if you put some kind of delta function, you can say that this potential here, this 4 legs thing, can be associated with a tetrahedron. And so in a sense, the Feynman diagram here is going to be the one complex dual to the triangulation. And this is some good idea introduced by Boulatov, which is actually a generalization of matrix models, where in matrix models, they use typically a phi cube, a cubic interaction, and the cubic interaction is basically generating a triangle because it's cubed, so it's got 3 edges, so it's going to be associated with a triangle. Here, it's, if we want to talk in 3D, we are talking about tetrahedra, and a tetrahedron has got 4 faces, so there's going to be phi to the 4. And so then, if you have 2 vertices, interaction vertices, then you can glue them through a propagator. And so that's going to be this geometrically, this is going to have the effect of gluing 2 tetrahedra together. And so the propagator here is going to be trivial in the sense that there is no p square, whatever. It's just an identity. It's just an identity thing. It's like just a mass. The mass would be 1 essentially. So I want to give you a concrete example. So I'm going to look at a scalar field. So I'm going to take it field for simplicity. So this is a model that was introduced by Boulatov, so 30 years ago. And I'm going to demand that this field is invariant under left translation. So to implement the invariance under left translation, what I'm going to do is that I'm going to translate each term. Okay, so that's a global translation. To make it invariant, I'm going to sum over all these possible translations. That's why I'm using the R measure. I'm summing over all this left translation. And so then in this case, the field is going to become, you can check by the invariance, because we're using the R measure, this guy is going to be invariant in the left translation. So there is a way, an interpretation to, understand that. Essentially, this G1, G2, G3, you can represent them as this structure over there, and H is going to be kind of perpendicular, right? So we have like the G's into the plane, and H is going to go in the third direction. And so the G's are basically associated with a triangle, and the H is going to be dual to this triangle. And so you see the color coding is the same as before. So this means that this H is going to be really encoding the one complex dual to the triangulation, where the triangle here would be part of the triangulation. So then we can introduce this interaction term. Like I said before, this interaction term is a 5 to the 4. So strictly, roughly speaking, it's that. But also we can also encode it in this way, so that different representation. This type of theories are basically studied by people doing tensor theory. Like I said, these models are generalization of matrix models, because now we have more indices, so that's becoming, this is actually a tensor theory. And this interaction term is not the standard 5 to the 4. You see, it's super non-local. Okay, so you see that here I got I got 12 G's, and the interaction term here, the delta, the identification is non-local. And so here the H's are the guys that are used to implement the left invariance, left translational invariance. And there is a way to interpret this geometrically. There is a way to interpret this structure. So I can look, for example, at this guy, and you see that this guy, if I look at this picture down there, this is just, I'm going to have H1, right? H1, G3, G4 minus 1, and then H2 minus 1. Oops, that's not the right thing. H2 minus 1 over there. So this guy is just implementing that this plaquette is actually a zero zero curvature. And each of these 6 deltas, they're implementing all the six plaquettes that I can draw here. And so I demand that these guys are flat. And so I told you before that this one field was interpreted as a triangle. And so here, since we have 4 fields, that's like 4 triangles. In fact, we can actually have the interpretation like that. So here you probably recognize. So in the face triangle here, I got this G here. This is my this is 1. So this G4, this G6. So that's probably this guy. And then I got the H that goes inside. So that's how I can interpret my this interaction term in a geometric manner. Now I got also to introduce a propagator, and the propagator is going to glue these terms. And I'm going to glue these guys. So this means that I'm going to take 2 vertices, and I'm going to identify them. And so this is just identifying the G's, right? So here that's just what I did with this, moving this guy there. I'm going to identify them, and once I can integrate them. They are all gone, and so this means that I can just erase them. And now I got 2 tetrahedra which are glued together. And that's basically this picture. And in this way, you see, I'm generating I got the triangulation, and I'm generating the dual one complex structure. And so if you glue down vertices like that, you can get some triangulation and the dual one complex at the same time. And for example, here, this is like a 4-point, I got 4 vertices here, and each of them are dual to a tetrahedron. And you see that now I get a dual face spanned by that. And this dual face, which is here, right? It's dual to one edge of the triangulation. And so like that, I can, with these Feynman diagrams, I can glue tetrahedra and construct a triangulation. Of course, when I'm going to glue that, it can be done in many arbitrary ways. So I'm going to get a lot of triangulations, which are pretty crazy and not nice manifolds. But that's fine. That's just the way it is. And so when you calculate the amplitudes, then you exactly recover this amplitude that we had before, which was, the fact that this plaquette here has zero curvature, and that's why is that? That's because when you glued, when we glue, when we glue here, we knew that one plaquette here we had this piece, right, that we got rid of. We knew that this plaquette here was flat, this other plaquette was flat, and we glued them, they are still flat, right? The remaining thing is flat. So we're only gluing flat plaquettes so that we get a flat plaquette. The big flat plaquette over there, this one is going to be flat. And that's why we're recovering, again, the Baratin and Oriti model in the delta formulation. So I'm a bit slow. So now what we'll have to do is to formulate this theory in terms of Hopf algebras instead. We'll use some abstract language nonsense to generalize this formulation so that then we can recover that in terms of the quantum group formulation. So we can introduce we can reformulate the projected field, which was the field which was invariant under the left translation. And so that's going to coincide with this expression. So it's a bit abstract, so I wanted to go through it. So here I've got 3 copies. So first I know that my field here is in 3 copies of H, okay? So if it's 3 copies of H, then I can evaluate this guy. I need, 3 copies of the group algebra. Then what I'm doing is the first thing here is that I'm doing the coproduct. I'm taking 2 copies of that. So I'm going to do the coproduct is going to go from H3 to H3 tensor H3. So that's what I'm doing. So that's really, this guy is going to be an element in H6. Okay, so, but I know that if I want to evaluate this guy, so I need 6 group elements here. And the coproduct dually becomes a product, right? So that if I want to evaluate, that's what I'm going to get. Fair enough. Then what I'm going to do is that I'm going to do this multiplication piece. And so what is this multiplication piece? So if you calculate, so you see that here, this is this guy. So this guy was 6, but then I'm doing some multiplication. So you can check out that at the end of the day, this new element is going to be in 4 copies of H. And then let's see what it means, that what are we doing here? So if it's in 4 copies, I need 4 group elements. And so I know that product here becomes coproduct. But this guy is only, you see that here I got 3 identities. So these guys are untouched, and this piece is only going to act on this H. And because of the structure here, I'm just going to get 3 copies because it's a group algebra, right? It's a trivial coproduct. So I'm just getting 3 copies of H. And then this coproduct here, that's just going to do the multiplication that I discussed before. So you see that this formula here is actually encoding the left, the global left translation that I introduced before. And then I can just integrate, right? So I don't do anything on the G piece, and I'm just going to integrate over this H sector, and that's going to be the left invariant field. Okay, so that's how I can formulate the this field that I introduced before, and then I can I can also take advantage of the fact that there is this Fourier transform, so I can perform a Fourier transform on that, and so here I can do the Fourier transform on the. I want to do maybe the Fourier transform on the fields which are defined on SU2 so that you get a sense of what's going on. So I'm doing a Fourier transform. So I got my plane waves here, and that's a field which is invariant under left translation. And then I'm going to use the left invariance of the measure. You see the H, I'm going to send it. You see that I got G's here. That's a Fourier transform. Then I'm going to just do redefine the fields. So I'm going to get only the H in here, and then I'm going to split the plane wave. And so then I'm going to, because H is common for each X, really I'm getting one H here and the sum of the X's on the other side, because it's just the abelian group. And then I'm performing all the integration. So this guy is going to become a delta function. And this is just the Fourier transform of this field. And so then I get this delta function, and that's saying that the sum of the x's is equal to 0. But I remind you that each x was actually an edge, and so that's just saying that the three edges they sum up to 0, so that's forming a triangle. We can also generalize this the interaction term in terms of the Hopf algebra language. And so time is running out a bit. So anyway, the formula are very complicated, so I didn't want to spend too much time. But really what we do is that we are dealing with the delta function that we introduced before. And then we have to implement this delta nu. Is just a short notation to say that we're looking at all these flat plaquettes. Or conversely, if we do the Fourier transform, you can rewrite this interaction term as saying that the interaction term just saying that we have 4 triangles, and these 4 triangles are basically glued together to form one tetrahedron. So this means that each edge, you see that this edge should be identified because it's an edge which is in this triangle, and it's also an edge in this triangle. So this is identification of the edge. That's saying that each C here is saying we have a closure constraint, we have 4 triangles, and now this guy is going to be encoding the fact that we glue these 4 triangles into one tetrahedron. So this is like this formulation. When you do the Fourier transform, you're like in a triangulation picture, whereas here we are in the dual one complex picture. The propagator, we can also formulate the propagator. Time is running out, so I'm just going to be quick. So then at the end, you can evaluate these amplitudes. And indeed, we're getting a generalization of the thing that I told you before with the delta function. And in fact, for example, we can get this formulation where this is a formulation for the, in terms of the one complex, we just get, a product of deltas. Here, there is 2n coproduct. You remember before I had n coproduct, that's because I was talking about links. But in this field theory approach, we're always talking about half links, right? Because we take a link is something that connects 2 nodes, but here we were always working with half links because we had the link was stopping here at the triangle. So it's when we are gluing the triangles, we get a big link. And so you can formulate this amplitude in terms of delta functions, and that's generalization of what I introduced before. And so then you can prove with this delta function formulation that the amplitudes are topological invariants in the sense that we can perform the Pachner moves and they are going to be proportional to each other with some adequate constants. So then this means that the amplitude that we are having here are basically the analog of the Girelli model that I discussed at the beginning, especially if you want to do that in the quantum group case. So we can do that. We can now apply this formula in the quantum group case, on the deformed quantum group case, and recover, the Girelli formula. I'm going to skip that because time is off. So the punchline is that I just wanted to emphasize again the well-known fact that the plane wave is kind of the root behind when the structure of a double, right? And so really what's important is that if you have a double, you have a duality between this structure, and out of this duality, you have this notion of plane wave. And then if you want to build this Girelli amplitude, then you can construct it in terms of plane waves or delta function. There is a formula for that. And then also something I wanted to convey is that you can use this field theory approach, Feynman diagrams, to actually generate this triangulation of these topological invariants. And there are some interesting things, of course, to do. Some of them is to include matter, so that would be introducing topological defects. Or here, I always emphasize a lot that I was doing Q-real, so that I don't want to deal with quasi-Hopf algebras. So quasi-Hopf algebras would have to be treated in, more carefully here. All my coproducts were actually co-associative, so there was, things were kept simple. And then, so that's a theory for 3D, but then one could wonder, how can you extend that to 4D? Well, it's well known that in 4D, one should not only use categories, but also two categories, in fact. And in this case, we should use two categorical structures. In fact, I think in 2018 or something like that, the analog of the Barrett-Westbury model was introduced in terms of two categories. And from the dual picture, we would expect to have two Hopf algebras, or more down to the earth, maybe two group structures. And in fact, I've been working on that also to generalize this formalism to two groups, which are just basically when you consider decoration on links, but also on faces. So you have one holonomies and two holonomies. But that's like an entire different topic. All right, thank you. That's it. Sorry, I was a bit longer than expected. Thank you.
Thank you very much. It was a nice talk.
Thank you.
Are there questions or remarks?
Yes, I may have a question. You are interested in two Hopf algebras in duality so that you can use this Fourier transform. In mathematics literature, there are some examples of self-dual Hopf algebras. For example, the non-commutative version of Kohn-Kreimer, described by Loïc Foissy, or the Malvenuto-Rautenauer Hopf algebra of permutations. Would it make sense to implement such Fourier transforms in that context?
I guess. I mean, the abstract nonsense should apply.
Yeah. Okay.
I'm not familiar with this Hopf algebra, so I'm not totally sure.
Well,
if it's they are also co-associative and so on, then I mean, abstract. If you have the duality map, then I think you could.
Well, they are rather mild because they are combinatorial, they are graded and connected. I mean, the degree 0 part is of dimension 1, so maybe it's simpler than through quantum groups in some sense.
Right, but I don't know. Would that be useful in some way? So, what would be would there be some application?
Yeah, I don't know. Just by curiosity.
Yeah, so I think if you can find a pair of algebras which are dual, so I mean if they are self-dual, then we know that there is a duality between itself. Then there is probably then yes, you can construct the plane wave and so on. I suspect that it's also something that is happening when Q is root of unity, because in this case. For SU2 Q of root of unity, because in this case the Chern-Simons theory is based on SU2 and SU2, so it's SO4, so it's two copies of SU2, and so then you need to have SU2 dual to SU2, so you have this pair of algebras which are the same, and but then things are complicated because there is this quasi structure that pops up. But I guess, I didn't study that, but I guess there would be some kind of self-duality here as well. But I didn't study that yet, so I don't really know what's happening.
Okay, thanks.
Thank you. Are there other questions or comments? Could you return one slide, Florian? So here you mentioned forward. Yes, group field theory and tensor models. Could you comment on this? So recently we have seen a few. I mean, not in the seminar, but I've seen talks about random tensors, the work of Gurau, etc. Sort of that.
Yeah. So Razvan
generalizes. Yes.
Yeah.
Sorry, please.
So Razvan basically actually all this work came up when he started to study actually this group field theory. So here, a group field theory, this is what Boulatov introduced, and this is really a field theory defined over a space which is a group, and that's the example I gave. And now what I was doing now is try to generalize that. So I was doing a field theory over a quantum group. That's my Hopf algebra field theory thing. So now these field theories, you can go to the representation picture, and then in this case, that's essentially like then using tensors, right? So you have, or you can see actually this when you deal with this. Let me show you. We can interpret, so there are different ways, but you can say that this, you see, this is kind of a phi. You can interpret this phi as some kind of some object which has three parameters, three indices, three labels, which are continuous, and then you can construct. You can say, oh, it's a tensor with continuous parameters. So it's a bit weird, but you could do that. Or you can actually go to the representation picture. And if you go to the representation picture using the Peter-Weyl theorem, which I discussed, where is it? So if you go use the Peter-Weyl theorem, then you can actually replace. Yeah, here you go. You see the field, you replace the field by an object which has labels which are discrete. So it's more looking like maybe it's more looking like normal labels for a tensor. And then you basically can play with those, and then you have like tensors. And so then what we're doing here is actually some kind of tensor model. And so it's some tensor models which have this property, which have these intrinsic properties where there is this left invariance to build up and so on. But so these models can be seen as a generalization as a matrix model. So in fact, if you are doing the phi cube case, the phi cube case would be exactly a matrix model. And so Razvan basically built up on that, and they studied. Yeah, so that it took that as a starting point and improved a lot. So that this opened up a new way. These models, these tensor models, this type of tensor models, there was a lot of expectation because it was hoped that they had some nice limit, but then at the end, the hope was not so realized, and so they don't behave so nicely when you take some large tensors, when you do these large n limits.
Mm-hmm.
But yes, that's these group field theories are a specific example of tensor models.
Okay, thank you. Maybe another question or comment? Okay. If this is not the case, then I suggest we thank the speaker again. Thank you very much.
Yeah, thank you for listening. I don't know if it was the same type that we are used to, same content. I hope this was still interesting.
Yes. It was interesting, yes. Okay, then I hope we have a nice weekend.
Thank you, and same to you.
Thank you.
Bye.
I have to travel tomorrow, so some challenge.
Good luck with that then. I'm actually I'm going to Ottawa now, actually.
Okay. Okay.
All right.
Then all the best. Thank you.
Thank you. Thank you very much.